Spring of 1944. A crashed American fighter lies crumpled in a field near Cambrai, France. The morning of June 6th, the day Allied forces stormed the Normandy beaches, Lieutenant Thomas Fraser of the 334th Fighter Squadron had lost his bearings during the intense fighter sweeps supporting the invasion. His P-51 Mustang, bearing the squadron code QPG and nicknamed Jerry, struck French soil hard. Fraser survived and would spend the rest of the war as a prisoner, but his aircraft, serial number 43-24825, was about to reveal something to German engineers that would fundamentally alter their understanding of American industrial capacity and the true scope of the challenge they faced. German salvage teams had perfected a systematic art by 1944. Specialized units called Bergebataillon operated across occupied Europe with remarkable efficiency. They secured crash sites, assessed damage, and transported repairable aircraft to centralized facilities before advancing Allied forces could recapture the wrecks. Fraser's Mustang, despite battle damage and the impact of the crash landing, remained largely intact. Within weeks, it was loaded onto rail transport and sent northward to Rechlin, approximately 100 kilometers northwest of Berlin in Mecklenburg. This was the Reich's primary aircraft testing and evaluation center, where the Luftwaffe's most experienced engineers and test pilots worked to understand every advantage the Allies possessed in the air war. What they would discover about this particular aircraft's capabilities would prove more troubling than any tactical assessment or combat report. The revelation would not come from the Mustang's speed, not from its maneuverability, not even from the sophisticated Packard-built Merlin engine that powered it. The shock would come from something far simpler, something that spoke to a disparity so fundamental that it called into question Germany's ability to continue the war at all. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The facility at Rechlin had served as the Luftwaffe's central testing ground since February 26, 1936. It featured extensive workshops equipped with specialized tools, comprehensive test ranges for various evaluation protocols, and runways specifically configured for controlled evaluation flights. By mid-1944, the systematic examination of captured enemy aircraft had become a critical function of German technical intelligence. Teams of engineers and pilots worked methodically to understand Allied capabilities through direct analysis, rather than relying solely on fragmentary combat reports. Fraser's P-51B-15-NA arrived at Rechlin in early summer. German technicians possessed considerable skill in reverse engineering and repairing Allied aircraft despite lacking original technical manuals, factory specifications, or genuine spare parts manufactured to original tolerances. The repair process required substantial ingenuity. They cannibalized components from other crashed P-51 seconds recovered across Europe, building an inventory of parts that could be matched and fitted to create one flight-worthy aircraft from multiple damaged machines. The Packard V-1650-3 Merlin engine underwent detailed inspection. This power plant, a license-built version of the Rolls-Royce Merlin 63, featured a two-stage two-speed supercharger that produced 1,490 horsepower at 13,750 feet. The engine represented significant technological achievement, delivering substantially more power at altitude than single-stage supercharged engines through its sophisticated intercooled supercharger system. German engineers examined it carefully, noting the quality of, quote, materials, the precision of manufacturing, the reliability of components. The aircraft's 450 caliber Browning M2 machine guns, mounted 2 per wing in the P-51B configuration, were removed and replaced with ballast weights to maintain proper weight distribution and center of gravity. German regulations strictly prohibited arming captured aircraft used for testing and demonstration purposes. Control surfaces were examined for structural integrity. Hydraulic systems underwent pressure testing. Fuel tanks were inspected for damage and potential leak points. After weeks of meticulous work, the Mustang emerged wearing German markings. Its fuselage bore the Luftwaffe code T9+HK, The tail and undersides received bright RLM-04 yellow paint for easy identification by German pilots who might otherwise mistake it for an enemy aircraft. The propeller spinner was painted yellow, and a red band adorned the nose of the engine cowling. Following standard Luftwaffe identification procedures for captured aircraft, this Mustang was declared ready for initial test flights. Hans-Werner Lersch, one of Germany's most experienced test pilots, had the opportunity to fly a captured P-51B in June of 1944, a different airframe than Fraser's, but the same model, the same capabilities, the same implications. Lersch approached the flight with professional curiosity. He had read the preliminary reports. The aircraft was clearly well designed, not just because of its engine, but also its airframe. Still, official assessments had consistently portrayed American aircraft as crude, mass-produced machines that prioritized quantity over quality. The cockpit layout immediately impressed him. German pilots familiar with the cramped confines of Messerschmitt Bf 109 cockpits found the Mustang spacious by comparison. Controls were logically arranged and positioned within easy reach, reducing pilot workload. Instruments were clearly marked, with easily readable gauges, sensibly grouped by function. The seat provided noticeably better comfort than German fighters, an important consideration during multi-hour missions where pilot fatigue could impact performance. Visibility, even in the earlier Razorback configuration with its framed canopy, exceeded what Bf 109 pilots experienced. But the true revelation came when Lersch advanced the throttle. The Packard Merlin responded with smooth, progressive power delivery. The power built steadily and predictably as the Mustang accelerated down Rechlin's runway. The takeoff roll was noticeably shorter than expected for an aircraft of the P-51's weight and size, a clear testimony to the engine's substantial power output and the airframe's efficient aerodynamic design that minimized drag. Once airborne, the Mustang demonstrated handling characteristics that fundamentally challenged everything German pilots thought they understood about American aircraft design philosophy. The flight controls were beautifully harmonized. Aileron, elevator, and rudder forces were perfectly balanced across the entire speed range. Control forces increased predictably with speed, providing good feedback without becoming excessively heavy. The Mustang responded crisply and predictably to control inputs, without displaying oversensitivity or nervous handling. Roll rate exceeded that of the Bf 109 significantly and approached the exceptional roll performance of the FW 190. German test pilots systematically evaluated the Mustang's performance envelope through carefully planned test flights. Climb performance impressed them considerably and generated significant concern about tactical implications. The P-51B could maintain excellent climb rates to altitudes well exceeding 30,000 feet, where the two-stage supercharged Merlin engine continued producing substantial power even as progressively thinner air severely degraded performance in German fighters equipped with single-stage superchargers. This concerned German pilots and tactical planners because American bomber formations typically operated between 25,000 and 30,000 feet. German fighters, equipped with single-stage superchargers, struggled increasingly to intercept effectively at these altitudes, their engines gasping for sufficient air, while the Mustang's sophisticated two-stage Merlin continued delivering robust, reliable power. The revelation proved sobering to pilots and commanders who understood the implications. The Mustang could not only escort bombers to these altitudes but could fight there effectively, maintaining speed advantage and maneuverability, while German interceptors labored with reduced power. Speed trials conducted under controlled conditions at various altitudes confirmed the Mustang's clear superiority. The P-51B could achieve approximately 440 miles per hour at optimal altitude with the engine running at military power settings, significantly faster than the Messerschmitt Bf 109G's approximately 386 miles per hour and the Focke-Wulf FW 190A's approximately 408 miles per hour when measured under comparable conditions. This substantial speed advantage proved tactically decisive because it fundamentally allowed Mustang pilots to dictate engagement terms. American pilots could choose when to engage, pursuing fleeing German fighters when the tactical situation favored attack. Equally important, they could choose to disengage from unfavorable encounters, accelerating away from German fighters that lacked sufficient speed to pursue. German pilots discovered they could not force combat on a Mustang, whose pilot recognized an unfavorable situation and chose to avoid engagement. The wing design of the P-51, based on NACA laminar flow airfoil sections, gave the Mustang its distinctive appearance and delivered exceptional aerodynamic efficiency. Though German engineers noted that achieving true laminar flow in operational conditions remained elusive due to manufacturing tolerances, surface imperfections, rivets, paint, and operational wear, the P-51's wing nonetheless generated substantial lift with minimal drag compared to conventional airfoils. This wing design maintained its effectiveness across a remarkably broad speed range, providing consistent, predictable handling characteristics that reduced pilot workload. Dive performance revealed yet another area where the Mustang demonstrated clear superiority over German fighters. The aircraft could dive at very high speeds without encountering the severe control stiffening that plagued many fighters. Pilots could pull out of steep, high-speed dives without requiring excessive physical effort, and the airframe remained stable throughout without tendency toward flutter or structural failure. German test pilots noted this capability with particular interest because diving attacks represented a primary German tactical doctrine. The Mustang's ability to follow German fighters through high-speed dives and maintain full control authority eliminated a key German tactical advantage. But all of these performance characteristics, impressive as they were, did not constitute the true shock that German engineers experienced at Rechlin in the spring and summer of 1944. The Mustang was a very good fighter aircraft. German pilots acknowledged this through their systematic testing. It was faster than German fighters at altitude. It climbed better. It dove better. It handled beautifully. These were tactical considerations, problems that might potentially be addressed through improved German designs or clever tactical doctrine. The revelation that fundamentally altered German understanding came not from what the Mustang could do in the air, but from how far it could fly before running out of fuel. And that revelation began with a simple question that German intelligence officers had been asking since early March of 1944, when American fighters first appeared over Berlin. How? The distance from English bases to the German capital measured approximately 560 miles one way. Standard fighter aircraft, even with external fuel tanks, could not carry enough fuel for such a mission while maintaining combat capability. This assessment had been based on analysis of earlier captured P-47 Thunderbolts and P-38 Lightnings, both of which had demonstrated limited penetration into German airspace before fuel constraints forced them to turn back. Yet, on March 4, 1944, P-51 Mustangs from the 4th Fighter Group had escorted bombers to Berlin. 2 days later, on March 6, approximately 660 bombers attacked Berlin in daylight, escorted by over 150 P-51 Mustangs. The escort fighters had engaged Luftwaffe interceptors over the German capital and accompanied the bombers home. This was not a fluke. The Americans had solved the escort fighter problem. General Major Adolf Galland, General der Jagdflieger, and one of Germany's most successful fighter aces with over 100 victories, had flown combat missions during this period despite his administrative position. He encountered P-51 formations over Germany and immediately recognized the implications. His combat assessments submitted through official channels noted that American fighters were operating at full combat capability over Berlin, engaging aggressively with no apparent fuel conservation behavior. They were not flying at the limits of their range. They had reserves. This contradicted everything Luftwaffe intelligence believed about American fighter capabilities. The technical evaluation at Rechlin focused first on determining how the Americans had achieved this range. The evaluation team measured the P-51B's internal fuel capacity. The aircraft featured 2 wing tanks, each holding 92 gallons of aviation fuel, for a total of 184 gallons in the wings. Additionally, the fuselage contained an 85-gallon fuel tank positioned directly behind the cockpit. This fuselage tank had been a relatively recent addition to the P-51B design, incorporated during production to extend range. Total internal fuel capacity was 269 gallons. The Packard-built Merlin engine consumed fuel at rates that varied with power settings. At economy cruise settings, the engine burned approximately 60 gallons per hour. At normal cruise power, consumption increased to approximately 75 gallons per hour. German engineers performed range calculations using these figures. With 269 gallons of internal fuel and consumption of approximately 70 gallons per hour at cruise settings, the P-51B could fly for roughly 3.8 hours, at the aircraft's cruising speed of approximately 300 miles per hour. This yielded a maximum range of 1,140 miles. This was precisely enough to reach Berlin from English bases and return, but only barely, with no reserves for combat operations. Yet combat reports clearly indicated the American fighters had engaged in prolonged dogfights over Berlin, sometimes lasting 15 to 20 minutes before disengaging and flying home. Combat power settings consumed fuel at rates exceeding 100 gallons per hour. Such fuel expenditure should have left the aircraft unable to complete the return journey. The calculations did not explain what German pilots were observing in combat. The answer became apparent when technical staff examined the aircraft's wing structure more carefully. The P-51B featured standardized hardpoints under each wing designed to accommodate external stores. These attachment points included fuel line connections, indicating they were designed specifically for external fuel tanks. Drop tanks were not a new concept. German fighters had used them since the Battle of Britain. The Bf-109 could carry a 300-litre drop tank. The FW-190 regularly employed them for extended range missions. Drop tanks allowed aircraft to carry additional fuel externally, then jettison the empty tanks before entering combat to reduce weight and drag. This was standard practice for all air forces. The question was not whether the Americans were using drop tanks, but rather what capacity these tanks had and how the Americans were producing enough of them to maintain operational tempo. The search for American drop tanks from the March missions began immediately. Intelligence officers plotted likely jettison points based on engagement locations reported by Luftwaffe pilots. Drop tanks would typically be released when enemy fighters were encountered, as the external stores reduced maneuverability and speed. Search teams composed of Wehrmacht personnel and Hitler Youth volunteers spread across the countryside northeast of Berlin, looking for any debris from the air battles. Within 3 days, several objects were recovered from fields and forests in the region. Most were fragmentary, crushed on impact or damaged by the fall. But 2 examples arrived at Rechlin in relatively intact condition, having landed in soft soil or winter wheat that cushioned their impact. The captured drop tanks revolutionized German understanding of American industrial methods. The tanks were cylindrical, measuring approximately 108 inches in length with a diameter of roughly 22 inches at the widest point. Capacity calculations indicated each tank held approximately 108 US gallons. 2 such tanks would provide 216 additional gallons of fuel, extending the P-51's total fuel capacity to 485 gallons. With this fuel load, the Mustang could fly for approximately 6.7 hours at cruise power settings, yielding a range exceeding 2,000 miles. This was more than sufficient for the Berlin mission with substantial combat reserves. The fuel capacity mathematics now made sense, but what captured the immediate attention of German engineers was not the capacity of the tanks, but rather their construction. The drop tanks were not made of metal. Running a hand along the surface revealed a texture unlike aluminum or steel. The silver paint coating the exterior could not disguise the fundamental nature of the material beneath. When engineers carefully scraped away a small section of the paint near the tail cone, they found multiple layers of heavy paper. Each layer, perhaps half a millimeter thick, compressed and laminated together with a resinous adhesive. The construction was sophisticated and purposeful. The nose cone and tail cone were formed from overlapping pieces of the paper material, pressed into shape like papier-mâché. Each piece was visible as a slight ridge where it overlapped with adjacent pieces, creating a scalloped texture. The center section was seamless, wrapped around a cylindrical form in continuous layers. The fuel fittings were brass, precisely machined and properly sealed. Peering through the filler cap revealed an interior coated with what appeared to be a cellulose-based lacquer designed to resist the corrosive effects of aviation gasoline. German materials specialists were brought in to analyze the tank's construction in detail. The paper was identified as kraft paper, manufactured using a chemical pulping process that produced exceptionally strong cellulose fibers. This was the same material used for heavy-duty shipping containers and industrial packaging. The adhesive proved to be a resorcinol formaldehyde resin, a thermosetting polymer that created bonds stronger than the paper itself when heat-cured. The lamination involved at least 12 separate layers of paper, each one carefully oriented to provide strength in multiple directions. Anti-slosh baffles made of wood were installed inside to prevent fuel from surging during maneuvers. The entire construction process was clearly standardized and designed for mass production. Most significantly, the empty tank weighed approximately 80 pounds, compared to 65 to 75 pounds for a comparable metal tank of smaller capacity. The paper construction was not significantly lighter than metal, but it offered other advantages. The implications were immediately clear to the technical staff at Rechlin. The Americans were manufacturing fuel tanks from non-strategic materials. Paper and wood-based resins did not require the aluminum, steel, or other metals that were increasingly scarce in wartime economies. The manufacturing process required no specialized metalwork equipment, no skilled metal workers, no welding or forming of sheet metal. These tanks could be produced in any paper mill or packaging factory with relatively simple modifications to existing equipment. The United States had hundreds of such facilities. If even a small percentage of American paper production had been converted to drop tank manufacturing, output could reach thousands of units per week. The tanks appeared to have no serial numbers, no manufacturer markings, nothing to indicate limited production. They were commodity items, mass-produced and completely expendable. Intelligence officers began researching American paper industry capacity. The United States produced approximately 12 million tons of paper annually before the war, with production increasing during wartime mobilization. Converting even 1% of this capacity to drop tank production would yield over 100,000 tanks per month, far exceeding any plausible requirement for P-51 operations. The real constraint would not be materials, but rather the availability of manufacturing equipment and labor to assemble the tanks. But this was precisely the type of manufacturing that could be performed by semi-skilled workers after minimal training. The paper tanks represented industrial efficiency and resource optimization on a scale that German planners found difficult to comprehend. Further analysis revealed additional details about the paper tank's design and use. The tanks were strictly single-use items. The resorcinol adhesive, while creating strong bonds when cured, was slowly dissolved by prolonged contact with aviation gasoline. Intelligence reports and interrogation of captured American aircrew indicated that paper tanks had to be filled immediately before flight and could not be stored filled for more than a few hours without developing leaks. This was not a limitation that affected operational use. Fighters were fueled as part of their pre-flight preparation. The tanks would be used for a few hours during the mission, then jettisoned. The single-use nature actually simplified logistics. There was no need to recover and reuse the tanks, no need for cleaning, inspection, or maintenance. They were expendable by design. The German evaluation also noted the color coding of the tanks. Paper drop tanks were painted silver, while metal tanks used by American forces were painted gray. This color distinction allowed ground crews to quickly identify tank types during fueling operations. The silver finish on paper tanks also helped reflect solar heat, reducing fuel evaporation and vapor pressure issues at altitude. Every aspect of the design reflected systematic engineering optimization for mass production and field use. By late March 1944, German intelligence had traced the origin of the paper drop tanks to British development. The Air Ministry in London had commissioned development of impregnated paper fuel tanks in 1943 to conserve strategic metals, particularly aluminum. The Bowater-Scott Corporation, utilizing expertise in paper manufacturing, developed the production process. The tanks entered service with RAF fighter squadrons in late 1943. American forces quickly adopted the design, with multiple manufacturers in both Britain and the United States producing tanks for use by USAAF fighter groups. The innovation had been driven by British resource scarcity, but was being exploited on a massive scale by American industrial capacity. The broader implications extended far beyond fuel tanks. German technical staff began a systematic review of captured American equipment, looking for other examples of industrial innovation and mass production techniques. The results painted a consistent picture. American equipment was not always technologically superior to German equivalents in terms of individual component performance. German optics were often better. German small arms were often more sophisticated in design. German armor metallurgy was in some respects more advanced, but American equipment was consistently better manufactured, more standardized, more reliable, and available, in vastly greater quantities. The American approach prioritized producibility over perfection. Components were designed from the outset for mass production by semi-skilled workers using standardized tooling. Parts were interchangeable between units without hand-fitting. Assembly line methods reduced production time and increased output. The contrast with German production methods was stark. German weapons and equipment were often technical masterpieces, hand-fitted by skilled craftsmen. A German tank or aircraft engine represented the peak of precision engineering, but building such equipment required skilled labor, specialized tools, and significant time per unit. Production rates were constrained by the availability of master craftsmen and precision manufacturing equipment. The Germans built superior individual items. The Americans built adequate items in overwhelming quantity. In industrial warfare, quantity had proven decisive. Analysis of P-51 Mustang production illustrated this principle. North American Aviation had designed the original Mustang prototype in response to a British requirement in 1940. The prototype NA-73X was completed just 117 days after the contract was signed, one of the fastest design-to-prototype cycles in aviation history. The first flight occurred on October 26, 1940. By 1944, North American was producing P-51 variants at 2 facilities. The Inglewood plant in California averaged approximately 364 Mustangs per month during peak production periods. The Dallas plant contributed additional production. Combined output across both facilities reached an average of approximately 574 P-51 seconds per month during 1944, with production accelerating throughout the year. Peak monthly production would reach 881 aircraft in January 1945. Each P-51 required approximately 15,000 individual parts manufactured by hundreds of subcontractors across the United States. The Packard-built Merlin engines were produced in Detroit at rates exceeding 300 units per month. Final assembly of a P-51D required approximately 22,000 man-hours of labor, but the production line system meant that completed aircraft rolled out of the factory at intervals of a few hours. At peak efficiency, a new Mustang was completed approximately every 2 hours. The scale and efficiency of this production system exceeded anything Germany had achieved. Messerschmitt and Focke-Wulf combined produced approximately 600 fighters per month in early 1944. Despite operating under emergency priority programs and utilizing forced labor, German aircraft production could not match American output. The resource implications were equally sobering. American aluminum production in 1944 reached approximately 1.25 million tons, equivalent to £2.5 billion annually. This represented a massive increase from pre-war production of approximately 164,000 tons in 1939. Germany's aluminum production, by contrast, peaked at approximately 250,000 tons per year and was declining due to bombing of production facilities and loss of bauxite sources. The Americans had approximately 10 times Germany's aluminum production capacity. The decision to manufacture drop tanks from paper rather than aluminum was not driven by metal scarcity. The United States had sufficient aluminum to produce every drop tank in metal if desired. Paper was chosen because it was cheaper, required less critical manufacturing equipment, freed aluminum for other uses, and could be produced more quickly with less skilled labor. This was optimization, not desperation. The psychological impact of these revelations spread through the Luftwaffe technical and operational communities. The paper and drop tank became a symbol of American industrial capability and the fundamental disparity in resources between the combatants. Captured examples were displayed at technical briefings for Luftwaffe personnel. Pilots transitioning to fighter units were shown the tanks and asked to calculate the implications for combat tactics. The message was clear. American fighters could now escort bombers anywhere in Germany. The previous defensive strategy of waiting for Allied fighters to reach their fuel limits and turn back was obsolete. Luftwaffe fighters would have to engage the escorts to reach the bombers, and those engagements would cost aircraft and pilots at rates Germany could not sustain. Galland provided operational assessments in conferences with senior Luftwaffe leadership throughout the spring of 1944. The P-51 was superior to German fighters above 20,000 feet, he emphasized repeatedly. It was faster than the Bf-109 at altitude, and more maneuverable than the FW-190. With the extended range provided by drop tanks, it could escort bombers throughout their mission profile. German fighters could no longer attack bomber formations unopposed after Allied escorts turned back. Every intercept now required fighting through the fighter screen. Loss rates were climbing steadily. In January 1944, the Luftwaffe lost approximately 90 fighters, while claiming approximately 150 Allied aircraft destroyed. By February, German losses had increased to approximately 160 aircraft against approximately 230 Allied losses. The trend was clear and unsustainable. The Americans and British could replace losses faster than Germany could inflict them. The summer of 1944 brought the full impact of American escort fighter capability. The 8th Air Force conducted deep penetration raids almost daily when weather permitted. Mustangs provided continuous escort, from England to targets across Germany and back. Luftwaffe fighter losses mounted catastrophically. In June 1944, approximately 350 fighters were lost defending the Reich. In July, losses exceeded 350 single-engine fighters in the West alone, representing a 31.2% monthly attrition rate. August saw similar losses with a 36% attrition rate. At these loss rates, experienced pilots were being killed faster than they could be replaced. The replacement pilots arriving from training schools had perhaps 150 hours of flight time compared to 300 hours or more for American pilots. Many German replacement pilots had as little as 30 hours in type before being assigned to operational squadrons. The experience gap, combined with numerical inferiority and the constant presence of P-51 escorts, made daylight operations over Germany increasingly deadly for the Luftwaffe. Galland submitted repeated assessments to Hitler and senior Wehrmacht leadership throughout this period. His September 1944 report stated the situation bluntly. The Luftwaffe could not win the air war. Germany lacked the resources, the fuel, the aircraft, and the trained pilots necessary to contest Allied air superiority. The Americans could replace losses faster than Germany could inflict them. Their industrial capacity was beyond Germany's ability to counter through combat operations. The only viable strategy was to husband remaining resources for defense of critical targets and hope for political settlement before complete collapse. The paper drop tanks continued to fall across Germany throughout late 1944 and into 1945. German civilians learned to recognize the distinctive cylindrical shapes lying in fields and forests. Initial reports sometimes described them as unexploded bombs, causing local panic until military authorities identified them as harmless. Fuel tanks. Instructions were distributed through civil defense organizations, explaining that the silver cylinders falling from Allied aircraft were empty fuel tanks, not weapons. The psychological impact was noted in civilian morale reports. The sight of enemy aircraft overhead in such numbers that their contrails crisscrossed the sky casually discarding expendable fuel tanks, reinforced the message that the Allies had resources to waste, while Germany scraped for every litre of fuel and every kilogram of aluminum. Technical intelligence continued analysing captured American equipment throughout 1944, but the focus shifted from understanding capabilities to documenting the scale of industrial disparity. Could Germany manufacture similar paper drop tanks? The technical answer was yes. German chemical industry could produce suitable resins. German paper mills could manufacture kraft paper. The manufacturing process was not particularly sophisticated, but the practical answer was no. Germany's chemical industry was already operating at maximum capacity, producing synthetic rubber, explosives, and other critical materials. Resin production for non-essential items could not be prioritized. The paper industry was fully committed to military requirements for maps, documents, and packaging. Most critically, there was no operational requirement for extended-range drop tanks. By late 1944, fuel shortages were grounding large portions of the Luftwaffe. Pilot training was reduced to minimal levels. Operational sorties were limited by fuel availability rather than aircraft availability. Building drop tanks to extend range was meaningless when there was barely enough fuel for local defensive operations. The irony was stark and bitter to German planners. The Americans had solved the fighter range problem with paper fuel tanks at exactly the time when German fighters were grounded by fuel shortages. Different problems, different industrial bases, different outcomes. The Americans had more of everything. More aircraft, more fuel, more pilots, more aluminum, more industrial capacity, and sufficient excess capacity to optimize solutions like paper drop tanks. Germany was fighting a war of scarcity against an enemy for whom scarcity was not a constraint. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Wanda Zirkus Rosarius, the specialized Luftwaffe unit that flew captured Allied aircraft, took Fraser's repaired Mustang coded T9 plus HK on an extensive tour to operational Luftwaffe fighter bases across Germany during late 1944. The unit's mission was educational, allowing frontline pilots to examine enemy aircraft firsthand, observe demonstration flights, and in some cases participate in mock combat sessions. At each stop, the captured Mustang would taxi past assembled German pilots and ground personnel, creating surreal scenes as an enemy aircraft bearing German markings moved among German fighters. Then came flight demonstrations where experienced German test pilots would fly the captured aircraft through carefully choreographed routines. For the Mustang demonstrations, test pilots would perform high-speed passes at low altitude to dramatically show the aircraft's significant speed advantage. They would execute climbing maneuvers to altitudes exceeding 30,000 feet to display remarkable climb performance. They would demonstrate the P-51's excellent roll rate through a series of crisp aileron rolls. Mock dogfights against German fighters would illustrate both the Mustang's strengths and the limited circumstances under which German fighters retained advantages. After the flying display concluded, pilots and ground personnel could approach the aircraft on the ground, examine it closely, inspect the cockpit layout, and ask detailed questions of the test pilots. These hands-on, educational sessions proved invaluable for demystifying enemy aircraft and providing concrete understanding of what German pilots faced in combat operations. The most valuable component of these base visits involved mock combat sessions, where captured Allied fighters would engage German fighters in carefully controlled simulated combat. Selected, experienced German pilots would fly their own operational aircraft against the captured types, experiencing firsthand how Allied fighters handled in dynamic combat situations. German pilots who participated in these mock engagements quickly discovered the extreme difficulty of successfully engaging a Mustang, whose pilot understood and properly utilized the aircraft's performance advantages. When German pilots pursued aggressively, the Mustang would simply accelerate away. When German pilots attempted to climb to gain advantageous position, the P-51 outclimbed them. When German pilots tried to force a sustained turning fight, where the Bf-1 109's superior turn performance should have provided advantage, The Mustang pilot would refuse the engagement by extending away using superior speed. The mock combat sessions proved sobering for German pilots who had believed their aircraft and established tactics remained reasonably competitive. Directly experiencing the Mustang's performance capabilities demonstrated clearly that American pilots flying P-51 seconds possessed significant tactical advantages, particularly at the high altitudes where bomber escort combat typically occurred. This pattern of revelation repeated itself across numerous Luftwaffe bases, where the Wanda Zirkus Rosarius conducted demonstrations throughout late 1944 and into 1945. The captured Mustang, designated T9 plus HK, served with the Wanda Zirkus Rosarius until December 10, 1944, when the aircraft and its pilot were lost. Historical records do not definitively specify whether the aircraft crashed during a demonstration flight or was destroyed on the ground during an Allied air raid. By that point, the aircraft had travelled extensively across Germany, visiting numerous Luftwaffe bases and providing direct education to hundreds of German pilots who gained invaluable first-hand knowledge of American aircraft capabilities. By January 1945, the war's outcome was beyond doubt. Soviet forces were approaching the Oder River, less than 50 miles from Berlin. Western Allied forces had recovered from the Ardennes offensive and were pushing toward the Rhine. The Luftwaffe could mount only sporadic resistance, limited by fuel availability and pilot losses. The systematic study of American equipment continued at Rechlin, but it had become an academic exercise. The findings were documented for the historical record, but they could no longer influence the war's outcome. The final comprehensive analysis of the P-51 and its drop tanks was prepared in late January 1945. The report documented every technical aspect of the Mustang's range capability, the drop tank construction methods and materials, production estimates, and operational implications. The conclusion was unambiguous. The P-51 Mustang, equipped with expendable paper drop tanks manufactured from non-strategic materials, has rendered the German heartland indefensible against American daylight bombing. Germany lacks the industrial capacity to match American fighter production, the fuel to sustain combat operations at the required scale, and the trained pilots to replace losses at current attrition rates. The report was filed in the Reich Air Ministry archives in late January 1945. Whether senior leadership read it is unknown. By then, technical reports analyzing American capabilities were simply confirming what battlefield reality had already demonstrated. The Luftwaffe, which had dominated European skies in 1940, was reduced to occasional desperate sorties by early 1945, hoarding precious fuel for missions that could not change the strategic situation. American fighters roamed freely over Germany, attacking targets of opportunity, escorting bombers, establishing complete air supremacy. Each paper drop tank falling from American aircraft was a reminder of the industrial disparity that had decided the air war. The story of German engineers examining paper cylinders of glued kraft paper, calculating fuel capacities, and recognizing the implications for the air war provides insight into how industrial capacity determines the outcome of modern conflicts. The war ended in May 1945. The systematic bombing campaign, enabled by long-range fighter escorts including the P-51 Mustang, had contributed significantly to Germany's defeat. Transportation networks were devastated, fuel supplies were exhausted, the Luftwaffe was reduced to a token force. Resulted from many factors operating over several years, but the ability to escort bombers throughout their missions over Germany, made possible by fighters like the P-51 carrying drop tanks, including those made from paper, was among the decisive elements. The paper drop tanks themselves, those that survived, became historical artifacts. A few found their way to museums. Most were destroyed or discarded. Their significance lies not in the objects themselves, but in what they represented. Industrial capacity applied with strategic purpose, appropriate technology solving specific problems, and the decisive advantage of overwhelming production capability in modern warfare. Post-war interrogations of Luftwaffe personnel consistently returned to this theme. When asked when they first understood that Germany would lose the war, many technical staff and senior officers cited early spring of 1944 as the turning point. The arrival of long-range fighter escorts over Berlin marked a decisive shift in the strategic balance. Hermann Göring, interrogated after the war, acknowledged that long-range fighters had delivered a major strategic blow to German defensive planning and were among the most decisive factors in the ultimate outcome of the air war. The technical lessons learned by German engineers who examined captured P-51 seconds and their drop tanks contributed to post-war aviation development. Many of these engineers immigrated to the United States or worked with Allied technical intelligence services after the war. Their detailed understanding of American production methods and design philosophy influenced their later work. The emphasis on standardization, interchangeability of parts, and design for manufacturability became standard practice in post-war aircraft development. The paper drop tank itself became a case study in wartime industrial innovation, taught in engineering schools and military staff colleges as an example of how resource optimization and mass production could provide strategic advantage. The P-51 Mustang continued in service with various air forces for decades after World War II. The aircraft saw extensive combat in the Korean War, serving primarily in ground attack and close air support roles. The excellent range and endurance that had made it an outstanding escort fighter in Europe proved equally valuable in the very different operating environment of Korea. P-51 seconds remained in frontline service with some air forces into the early 1980s, testament to the soundness of the basic design. More than 15,000 Mustangs were produced during and immediately after the war, making it one of the most numerous American fighters of the era. Today, over 100 P-51 seconds remain airworthy, maintained by collectors and museums worldwide. The sight of a Mustang in flight, often still wearing the distinctive markings of wartime units, serves as a reminder of the aircraft's role in establishing Allied air supremacy over Europe. The broader historical significance of the P-51 and its paper drop tanks extends beyond their tactical and operational impact. They represent a case study in industrial warfare and the importance of production capacity in modern conflict. World War II was decided not primarily on the battlefield, but in factories. The side that could produce more weapons, more ammunition, more aircraft, more vehicles, and more supplies faster than they were consumed in combat held a decisive advantage. The United States achieved industrial mobilization on a scale unprecedented in history. Peak wartime production in 1943 to 1944 saw American factories producing aircraft at rates exceeding 50,000 per year, ships at rates of multiple vessels per day, and ammunition in quantities measured in billions of rounds. This industrial output supported not only American forces, but also supplied substantial quantities of equipment to Britain, the Soviet Union, and other Allied nations through Lend-Lease. Germany, despite possessing significant industrial capacity and technical expertise, could not match Allied production. The reasons were multiple: smaller industrial base, strategic bombing of production facilities, loss of access to raw materials as territory was lost, diversion of resources to competing priorities, and inefficiencies in organization and planning. But perhaps most fundamentally, Germany was fighting a coalition whose combined industrial capacity was several times larger than its own. The addition of American industrial might to the Allied cause in 1942 to 1943 made Axis defeat inevitable once that industrial capacity reached full mobilization. The paper drop tanks falling across Germany in 1944 to 1945 symbolized this industrial reality in a form so simple and so stark that its message could not be misunderstood. A single P-51 Mustang was a very good fighter aircraft. 10,000 P-51 Mustangs represented air superiority that no tactical skill or technical innovation could overcome. This lesson, learned at great cost by Germany and Japan in World War II, influenced military planning throughout the Cold War and continues to inform strategic thinking today. The ability to sustain production of advanced weapons systems, to maintain supply chains under stress, to train personnel faster than they are lost in combat, and to outproduce an opponent over extended periods remains as critical now as it was in 1944. The March 1944 missions to Berlin, the first to be escorted all the way by single-engine fighters, marked a decisive turning point in the air war over Europe. From that point forward, no target in Germany was beyond the reach of American bombers with fighter escort. The systematic bombing campaign could proceed with losses that, while still significant, were sustainable. German war production came under increasing pressure. Synthetic fuel plants, ball-bearing factories, aircraft production facilities, and transportation networks all became targets that could be attacked repeatedly with fighter escort throughout the mission. The cumulative effect of this campaign, combined with Soviet advances from the east and Allied advances from the west and south, brought about Germany's defeat 14 months after the first P-51 seconds reached Berlin. The legacy of the paper drop tank extends beyond its wartime use. It serves as a reminder that effective solutions need not be sophisticated or technically impressive. A tank made from glued paper, designed for single use, manufactured from non-critical materials, represented an appropriate solution to the specific problem of extending fighter range. It was good enough for the mission. This principle, designing solutions that are adequate for purpose rather than pursuing technical perfection, became a fundamental concept in modern systems engineering. The best solution is not always the most sophisticated. The best solution is the one that meets requirements while being manufacturable in the quantities needed, within the time available, using accessible resources. This lesson, taught by paper drop tanks falling across Germany, remains relevant in military and civilian applications today. 80 years after the events of March 1944, the lessons remain instructive. The examination of captured equipment by German engineers at Rechlin revealed not just technical details but strategic realities. The paper drop tanks demonstrated that the United States possessed industrial capacity beyond Germany's ability to match, that American engineering emphasized practical solutions over technical perfectionism, and that the Allies had sufficient resources to optimize for efficiency rather than make desperate substitutions. These revelations, coming in March 1944, when the war's outcome was not yet certain but the trajectory was increasingly clear, provided German technical staff with clear understanding of the challenges they faced. That understanding could not change the outcome. Germany's defeat was determined by factors beyond the control of engineers at testing facilities. But the story of those engineers examining paper cylinders of glued kraft paper, calculating fuel capacities, and recognizing the implications for the air war provides insight into how industrial capacity determines the outcome of modern conflicts. The story, preserved in technical reports from Rechlin and other archives, continues to inform understanding of World War II and the nature of industrial conflict. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.